need water or anything? You good?
No. Cool. You good? All right. Hello, everyone. Today I'm going to talk about three-dimensional blockchain scaling with Cosmos and Tenement. It touches on some parts that Carl talked about earlier, but it also introduces some new and maybe slightly different concepts on like possible solutions to scalability within blockchains. Oh, and yeah, I'm also very sorry for like the clickbaity title. We thought of it last week, and to us it sounded very funny, and I still stand by it. It's like it kind of describes what I'm going to talk about, because I'm going to talk about three different things we can do to scalability. Oh yeah, so I'm Adrian, and I'm also working on the Cosmos project. So yeah. Next slide. Right, so today I'm going to talk about three-dimensional blockchain scaling. And you can already see the three dimensions here. So I'm going to talk about consensus scaling, state machine scaling, and interchange scaling. And just as a brief recap of what a blockchain really is, like when you look at Ethereum or Bitcoin, for example, a blockchain is like not this monolithic stack. We implement it as a very monolithic stack up until now. But really a blockchain is that you have peer-to-peer consensus, or peer-to-peer networking at the base layer, then you have a consensus layer on top, and then you have a state machine layer on top of that. So that's really what Ethereum, what a blockchain is. So in the case of Ethereum, you have libp2p as the networking stack, you have proof of work as a consensus layer, and finally you have the EVM as a state machine on top of all of this. And so users, it's like, if you're a developer, you either have the choice of building your own state machines or building on top of existing state machines. And then interchain scaling is all about how do we have multiple heterogeneous blockchains and how do they interoperate. And lastly, I'll talk a little bit about the modes of security that blockchains can operate in. So like the main thing I want to convey today is like, I'm not telling you exactly how to scale. Like I'm just like explaining a bunch of options that developers have in order to scale their decentralized applications. Yeah. So these are my three main goals for the talk. And like, I know it's early in the morning. Some people might have not had their second coffee by now. So it's like, if you only take something away, like only take away these 3 points. It's like the different approaches to scalability. We can either scale at consensus, at the state machine level, or at the interchain level, and I'll go into much more detail on all of them. And for the security modes, you can either choose a sovereign model, so something akin to Ethereum or Bitcoin, where it's a completely independent chain, a hosted model, where you share the security with some other chains, so you share a common validator set, but you still have heterogeneous blockchains, and a plasmag chain. Oh yeah, and lastly, and I think like, if you are currently writing decentralized applications, it's like, I would recommend that you don't just like sit around and hope that someone else solves your scalability problems. It's like you as a developer, it's really your responsibility to go out there and see what are the potential scaling solutions that I can use right now to build my applications. It's like don't just hope that someone solves scaling eventually. Actively look for solutions that you can use today to scale your applications. So I will briefly, yes. So I'll start with consensus scaling. So Nakamoto consensus, like traditional proof of work, chain-based consensus, where the longest chain is the correct chain. The reason why we need to have quite large block times is because we need to have the safety margin, where the propagation, so like generally speaking, the way blockchain works is that you start with a block, you validate that block, and then you kind of try to create a new block on top of this. And then once you have created a new block on top of this, you need to propagate it to everyone else in the network so that all the other participants know about that block. The reason why we have to have quite large block times in Nakamoto consensus is that in order to be safe, we have to give this leeway that we might have very long network latencies. Because if there's very long network latencies and they overtake the block time, we come into the scenario where we start having a split brain scenario. So that's a fork, right? It's like if it takes you longer to propagate a block to the network than it takes you to produce a new block, the network will start to have diverging opinions on the block. And realistically speaking, diverging opinions, like forks within the blockchain, are a terrible user experience. It's like no user expects to press a button and then to find out 30 minutes later that this got reverted. Like, this is not how anyone thinks about how the internet works or how any sort of application works. So like this ability to never go split brain is really important. And so this has been the traditional consensus layer, so Nakamoto consensus. BFT consensus, Byzantine fault tolerant consensus, it's a quite old research area, but it hasn't been applied to blockchains much as of late. The nice thing about it is that we're always safe. So we never go split brain. Due to that, we can push block times massively lower. They can just be optimally larger than network propagation takes. And even if the network latency becomes higher, instead of producing forks, we just start slowing down the network. So network latencies increase across the network. We just become slower at producing blocks, so our block times just increase. But in the normal case, this allows us to drastically reduce block times. So Bitcoin is at 10 minutes to give you the safety margin, that you're not splitting too much, and that the current miner doesn't have too much of an advantage over everyone else. And Ethereum is at like 15 seconds. Yeah, time seems reasonable. All right. So I want to talk a little bit about tenement consensus. And tenement consensus is a BFT algorithm. It's like from 2014, we've been developing it since then. And it has a bunch of nice properties. So it has instant finality. As soon as you send a transaction and it's included in a block, this transaction is completely final. There will not be a fork, at which point the user will be presented a different state of the network than he saw when he saw the transaction for the first time. So complete finality within one block. The other nice thing is that you have extremely efficient light clients. So in traditional Nakamoto consensus, you kind of have to keep up with the headers to verify that you're on the longest chain. In BFT consensus and tenement consensus, you have to be able to update your validator set, so the people validating the network. And you have to be able to update them like once every 3 weeks, kind of depending on your security assumption around unbonding and proof of stake. Moreover, it's safe in an asynchronous network, so we never become unsafe. So it prioritizes safety over liveness. And we have liveness in a partially synchronous network. So if you have the assumption that eventually we will have these messages will get delivered, we will always make progress. The incredible thing is that with this as a consensus scaling solution, we can have block times of 1 second. So we can have, let's say, 100 validators around the world. And I'll come later back to like how these validators get selected. But it's not as bad as it sounds. It's like not these 100 authorities, but rather these people are elected through economic stake. And so like everyone in the room that has a tiny amount of this economic stake is able to vote on who these, is able to delegate the economic stake to someone else. Oops. Is able to delegate the economic stakes to someone else and participate in the consensus. At the same time, this gives you like, at the peak, if you have 64 validators and like beefy data centers, this gives you about 4,000 transactions per second. So like think about the scalability increase that you get from switching to BFT consensus. Like one of the downsides is you have quite high network overhead. And like some future improvements we're working on, it's like BLS signatures, so we can aggregate votes on the network stack or the peer-to-peer network layer, so that we reduce this network overhead. Optimistic pipelining to get even higher transaction throughput and DKG constructions, decentralized key generation, which would allow us to like prevent validator front running. And maybe the last part is like, this is available right now. So we have an implementation called Tenement Core. And if you want to build your own blockchain on top of this consensus, you literally only have to write the state machine. And even that like is much easier with the tooling we've developed. So like, instead of having to worry like, or fork some other code base, the only thing you do is you take Tenement Core and you say, this is the exact application logic I want to build, and then build it on top of it. And you get the consensus and the networking for free. Is there anything else? I am. But of course, so if you're using tenement consensus, actually the limiting factor isn't the consensus anymore. The limiting factor is the state machine, right? So like the EVM or the UTXO set that you've built on top of the consensus. And like what we can get in terms of state machine scalability, like you can simply look at parity versus geth. So parity is about 2.5 times faster. So like there's a lot of room for optimization within state machines. And I'm also going to make another bold claim. I don't think most people should build like super specialized application directly on the EVM. The EVM was designed for smart contracts, not for smart, like it's a great use case if you need to deploy low transaction volume, one-off things like actual contracts. If you want to build a DEX or something like that, you're most likely much better off building it into a specialized state machine because you have all the optimization and like you can do whatever you want to the state machine. So you can design your complete protocol and you have complete freedom in how you build this. You're not constrained by some block gas limit or the gas cost. So like, and I think for most applications there's a real downside with like, the EVM is great if you need user level scripting. So if you need user level Turing completeness. Like imagine if you are building an application that requires the user to deploy their own smart contracts to interact with that application, the EVM is amazing. But if the only thing your user does is like send a transaction, there's no reason why you need to carry all this extra cool stuff with you to like just build this one specific application. And like removing all this cool stuff around you like reduces the attack surface massively that you have to face. And like it's much easier to reason exactly about what your state machine does. And at the same time, it's more scalable because you don't have to run all this extra code. So yeah, in conclusion, the EVM is amazing if you want to deploy contracts. If you want to build DEXs, I don't think it's your best bet. So, but even the EVM, like we can scale the EVM quite a lot. So we've built something called Etherment, which is essentially an EVM put on top of tenement consensus. So right, we have now these 4,000 transactions per second that we can have on the consensus level, and now we have the state machine as the EVM. And it's fully Web3 compatible, so like all the existing tooling works. It's already fully proof of stake. So it's like, it's something that you can try it today. The cool thing that once you put the EVM on like a BFT consensus algorithm is that it gives you, first of all, much higher transaction throughput, and secondly, extremely efficient light clients. So if you want to build a phone app that is that securely interacts with Etherment, for example, you have to come online once in like every 3 weeks. So you have to do like one header update once every 3 weeks. That's it. You don't have to constantly keep up with all the headers, which for mobile devices is massive. So due to the fact that Etherment like tenement consensus supports about 1 second block times, this is roughly 15 times as fast as current Ethereum, and so at the same block gas limit, we have about 15x the throughput. And like there's nothing, so like this is a different kind of assumption that, like if you remember Vlad's triangle from yesterday, Vlad was all about how you can have fewer nodes, a lot of nodes, and so the argument with tenement consensus is that you can have fewer nodes, so in the hundreds, but these nodes are fairly selected through economic majority votes, essentially, or delegation, by the entire stakeholder system in the chain. yeah, so that's Ethermint. That's a quick introduction. It's like essentially if you need fast smart contracts, this is a good bet. But I was talking about how we should make it easier for people to build their own state machines. And this is really what the Cosmos SDK is. The Cosmos SDK, you can imagine it's sort of like NPM, but for blockchains. So it allows you, it's a bunch of but by the way, it's not that nice yet. It's like NPM is pretty awesome. It will take us a while to get there. But you can imagine it as being able to pull different modules that you need. So for example, if you want to build a proof of stake system, you pull in the staking module. If you want to build a governance, like if you need governance, you pull in the governance module. If you need some way to do signature checking, so authentication, you pull in the auth module. And if you need the EVM, you pull in the EVM module. So like it really gives you this ability in very few lines of code to build your own state machine. Previously, this was extremely hard, right? Like most projects that are currently active essentially ended up forking the Bitcoin C++ code base and just like, yeah, we'll just modify it a little bit. Like we modify the state machine a little bit to do exactly what we want. But they still had to fork the entire code base and now have to live with, like, it's not a nice development experience. It wasn't something that everyone could do. With the Cosmos SDK, you can literally build Bitcoin and proof of stake in mostly like 200 lines of code. Of course, the SDK isn't done yet. It's like we've written this in Go, and in the future, we're hoping to add multiple languages to it, and also like add different VMs as modules, so that instead of having that you just have the choice. Like there can be an EVM module, there can be a WASM module. Different VMs can all you can decide which ones you want to pick. Of course, state machine scaling doesn't give you full vertical scale. It only gets you so far, right? Because we're still talking about scaling one blockchain. So, and I personally don't see a future in which we will have one homogeneous blockchain that runs everything. Most likely what will happen is that we'll have application-specific blockchains where, for example, like we had this example of Visa. I don't think Visa will build their payment processors within the EVM. I think they want something dedicated that they fully understand, that they fully build. No matter whether they open sourced it and have a decentralized validator set running it, but in my mind, we will end up moving towards a world of heterogeneous blockchains. And also like things like state channels totally work with either of these concepts. So because state channels are amazing, so it's like this doesn't limit you. So now I want to talk a little bit about interchain scaling. And interchain scaling is really, we have a future of heterogeneous blockchains. How do we make sure that these blockchains actually are able to talk to each other? And again, like this is, most likely we won't have a homogeneous future. Like different developers and different projects will want different trade-offs, and they don't want to be restricted to the same platform. It's like, yeah. So what IBC allows you to do is to do secure transfers between different blockchains. IBC relies on this notion of finality, that like we don't get reorgs, or like that IBC relies on the fact that your blockchain needs to have deterministic finality. So we can't have this Nakamoto consensus finality where we say it's probabilistic and like eventually nothing will get reverted anymore. We actually need true finality. And then the way it works is that both these chains are light clients to each other. So let's say you have chain A and chain B, and both of them are tracking each other's validator set so that they can receive messages signed by the other chain and verify the authenticity. And like again, this sounds crazy, right? Because light clients generally still require a large amount of headers. But again, like if you have like within proof of stake and with finality, you can probably get away with like doing a validator set update every 3 weeks, roughly, like every unbonding period in proof of stake. And so then the way it works is essentially on blockchain A, you lock some tokens to the consensus of blockchain B, construct a Merkle proof over that fact, and then send that Merkle proof or some relay process can send, like anyone in the world can send that relay, that packet to blockchain B, and blockchain B knows about the validator set of blockchain A, so they can verify the authenticity of that message. And now they're 100% certain that there are some tokens locked on blockchain A that blockchain B controls. So they can now give these tokens to other users. So currently, this supports tokens. We're hoping to extend this, or we're extending this to NFTs later this year. And the ideal world, once we get there, is that it supports complex objects so that we can take, for example, blockchain A can issue a loan, and we can move the entire loan with its complex internal stake over to blockchain B, and then interest payments can happen on blockchain B. And now, but of course, we don't live in a world yet where every blockchain has finality. So like Bitcoin and also Ethereum, and like all proof of work chains essentially have this probabilistic finality. And this is where PEGI comes in. PEGI is an adapter that essentially enforces finality over probabilistic chains. So it says that, let's say PEGI supports, so it listens to the blockchain and finalizes those blocks, like after 100 blocks, after you didn't get a revert, it's essentially the validator set says, okay, now I trust that this block is finalized. And this allows us to bridge proof of work chains into this finality IBC ecosystem, where we can, for example, we can send tokens between Ethereum and Bitcoin, given that we have two adapters for each of those chains. The reason why, the scariest thing here is that we have to enforce this 100 block threshold. And a lot of the questions are like, what happens if there's a reorg after 100 blocks? In my mind, this is not a huge issue anymore, because I thought about it some more, and if we actually have a 100 block deep hard fork, reorg within Ethereum, we will most likely have 2 Ethereums. Most exchanges use a confirmation between 6 and 12 blocks. By the time 100 blocks have passed, they've moved millions of dollars, and there will be massive major economic incentives to maintain 2 forks. That's even though it sounds scary, it's in reality this will probably be fine. But given this scenario of a lot of heterogeneous chains, one of the problem becomes, one of the niceties of having one chain is that you have a lot of liquidity within that chain, because everything is within that ecosystem. So once we start having this world of heterogeneous chains, we need some way to provide liquidity to people. And this is really what the Cosmos Hub is about. It's a liquidity provider for connected blockchains so that they can all tap into the same liquidity pool. At the same time, it's a double spend protection mechanism between blockchains. So Ethereum has this cool property that users can't double spend each other, right? It's I can't send my coins to 2 people, and those 2 transactions won't end up in the same chain, so I can't generate money out of thin air. The hub has exactly the same job, but between blockchains. So the hub maintains that 2 blockchains can't double spend each other. And so now we're moving into modes of security. Modes of security is really, you as an application developer, you can choose what kind of security model fits you best. It's this is not about describing which one you should pick. There's these are the different options that you have. And depending on your use case, one might make more sense than another. So the first one is sovereign, right? So sovereign is the basic default. It's probably the hardest, but it also gives you the most control. It allows you to change, it allows the stakeholders within that chain to change everything they want about how that chain operates. So this is kind of like the Ethereum Foundation running the EIP process and upgrading Ethereum at the doing the hard forks for Ethereum. It gives you the ultimate control over you as a developer. So for example, if you want to build a true DEX, And by the way, I'm just using DEX as an example because I think DEXs are pretty cool and they will be very big in like, no, I can't say that. They will, no recommendations here, guys. But given that, like, you want to build a DEX, right? So you have this, maybe have some staking, like you need to come up with some staking token that defines who the stakeholders are within your system. And then these stakeholders get to vote on every single aspect of that DEX. Whereas, and like this is the major difference to the hosted model. As in the hosted model, you kind of assume, like maybe a good comparison is like you own your own servers, or you're running on like virtualized instances in an Amazon data center. Like hosted is more like that, where you have to trust that the stakeholders of, or that the validators, the economic stakeholders, the people running your underlying security mechanism are doing the right thing and are doing protocol upgrades that aren't breaking to you. And maybe your use case might be too niche actually, so it doesn't fit with them, and then eventually, so I'm a big fan of the sovereign model. But like hosted is like the nice thing, you share the security. Like you can share underlying security assumptions with the other validator set. And lastly, Plasma. And so within Plasma, right, Carl talked about a bunch, like you all have the same security, like in every single child chain, you have the same security assumption than in the root chain, which is great. And I honestly, like a lot of things should possibly be Plasma once we have generalized, like general state transitions for Plasma. Because like building things within a UTXO model is very hard. But once we have general state transition, like general fraud proofs of an arbitrary state, we can like use Plasma a lot. Yep. Oh, actually, but like actually no, that's fine. So this is actually like getting very close towards the end of my talk. I just want to quickly recap the goals I talked about earlier. So like understanding the different approaches to scaling. So we can either scale consensus, and that already gives you a massive improvement. And like one of the nice things is it's out there right now. There's an implementation of tenement consensus within tenement core and within the parity client. So like if you're thinking about building a major application, you should really think about building it directly on top of a very scalable and very safe consensus algorithm. Oh yeah, and one of those things I actually forgot to mention, I think, it's like tenement prioritizes safety over liveness. So like, it never forks, it just halts until you can figure out why you would have forked. Which, like in my mind, for most financial applications, this is probably the preferred mode of operation. That instead of, oh, we have some sort of network, like we have some sort of network level attacker, and now we just start forking when we have two competing histories, and like we'll throw one away. It seems to me much safer to like figure out what's going on and then resolve that problem, and then you're live again. The second thing is state machine scaling. It's like it's getting much easier right now to build customized blockchains. It's not as hard as it used to be. Like that's the main thing. Like building your own application-specific blockchain is getting massively easier right now, and it will continue to do so over like the course of the coming years. So, if you're some sort of like heavyweight application, it makes a lot of sense to start looking into building your own application-specific blockchain, and then picking a security model that's right for that. And the last part is, even in a world of heterogeneous blockchains where everyone starts building their own chains, we still have the possibility to communicate between those. And we still have the possibility to access a lot of liquidity. So again, know the available modes of security, so sovereign, hosted, or Plasma. And like, I really want to drive this point home. It's like, scaling is everyone's responsibility. There is like, if you're writing a Solidity smart contract and you're just hoping it scales, like, I don't think you're doing your users or your project a service. Like, really think about what is my application and how can I scale this to potentially millions of users. So like, you should be actively looking for design patterns that allow you to build scalable dApps. decentralized applications. Yeah, scaling is everyone's responsibility. Don't wait for someone else to solve it for you. And then that's it. Thank you very much.
Validating transactions has become an unsurmountable burden for the little guy, simply because if you want to become an Ethereum validator, like your hard drive can't write as fast as the state grows. So